Hi, Algebra 2 friends. We're in section 11.4. We're going to talk about geometric series. In the same way that algebraic sequences are related to algebraic series, geometric sequences are related to geometric series in much the same way. So if I were to have the geometric sequence of 2, then 4, then 8, then 16, then 32, and I were to ask you to add up these values, this would be considered a geometric series. So geometric series is the sum of the values of a geometric sequence. So we'll use this geometric series or this geometric sequence to talk about series and to talk about the sum of the first n terms of a geometric series. So this is obviously 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, and the terms that we're dealing with are a sub 1 all the way up to a sub 5. The r value, the ratio, the common ratio in this case would be 2, and so we have all the information we need to apply these two simple formulas. So the first one says, and they're both formulas that relate the same information, so we're still finding the sum. If you look, S sub n is equal to the initial term, a sub 1 minus a sub 1 times r to the nth power. The number of values that we're dealing with is 5, so r to the 5th power. So 2 minus 2 to the times 2, which is r to the 5th power, is what we have here over 1 minus r, which is 2. And in this case, I should have this erased, and I should indicate that we're finding s sub 5, which is the sum of the first 5 terms of this sequence. And with a bit of computation, 2 minus 2 to the 6th, which is really 64, 2 minus 64 is negative 62 over negative 1 is equal to 62. That's what we get for the sum here. Let's see if that's true. So when I add 2 and 8, I get 10. And when I add 4 and 16, I get 20. And 10 plus 20 is 30. And 30 plus 32 is 62. How cool is that? So we could have used this formula, which we just did, or the other formula, which says that s sub 5 would be equal to the first term, 2 times 1 minus the r value, that's 2 to the 5th power, and that's over again 1 minus 2. And you can see that with a little distributive property, you would have gotten exactly the same thing. So I'm not showing you anything particularly interesting by saying that this is 2 times 2 to the 5th power is going to be 32. 32 minus 1 is going to be a negative 31, if you catch my drift, negative 1. And we see we get the same thing, negative 62 over negative 1, which is still 62. What's my point in doing that? I want you to recognize this formula, know that it works, and be ready to use it. So here's our first example. Example 1, find the sum of the first n terms. In the book Roots, author Alex Haley traces his family history back many generations to the time one of his ancestors was brought to America from Africa. If you could trace your family generation back for 15 generations, starting with your parents, how many ancestors would there be? So we're starting with our parents, of which we are generally having 2. And so we are going to be adding 2, and the next number that we add would be 4, because each of our parents have 2 parents. So the next number would be 4, and then the next number would be 8. You see what we're doing. And so we need to do this all the way back to for 15 generations, right? So we need to get all the way back to 15. So we're going to use the formula that we were just introduced to. And the reason why we're using this formula is because it is going to give us the sum of all of the ancestors all the way up to a sub 15, and that's what we want. So we need to fill in some information. First of all, we're looking for s sub 15, and we are going to tell you the initial value is 2. 1 minus r. What is r? What are we multiplying? Each time we are multiplying by 2. So it's going to be 2 to the 15th power. And all of that is going to be over 1 minus 2. And this is going to require a calculator. I don't hold this value in my mind so readily. So with your calculator, I would expect you to take 1, subtract 2 to the 15th power. So using a calculator, we get negative 32,767 in here, and then we multiply it by 2 for the grand total of, and dividing it by -1 for the grand total of 65,534. And that's a lot of ancestors there. It's always weird when I see the power of 2 doing something like that. Let's check out another example. Here in example 2, we're going to be evaluating a sum written in sigma notation. So we remember sigma notation from the last time when we talked about arithmetic series. Much the same is happening here. If you notice, these index numbers indicate that we are adding from 1 or adding from a sub 1 to a sub 6. So you kind of have that image in your mind. So technically we're looking for s sub 6. Does that kind of make sense? So if that's the case, we're going to pull out the same formula that we had before, which said, let's see, that s sub n is equal to a sub 1 times the quantity of 1 minus r to the n over 1 minus r. And so we need to figure out what these values are in order to satisfy this problem. So the way we'll do this is by saying, okay, we're trying to find s sub 6, or summing all the way up to s sub 6. And then we know that the first term, think about the first term. If I put 1 in here for the first term, I have 2 to the 0. The first term would be 5. So with s sub 1, or a sub 1 rather, being 5, and then 1 minus r. What is the r value? What is the value that we're constantly multiplying? And that value is going to be 2. So this is 2 then to the n power, 6 power, and then at the bottom I'm going to have 1 minus r, which is 1 minus 2. And so I'm going to complete this problem by calculating. I can use a calculator, obviously. 2 to the 6th power is going to be 64. So 1 minus 64 is a negative 63. I'm going to multiply that times 5, and then I'm going to divide it by a -1. And so I can do this. Let's see, 3 times that's going to give me 5, carry my 1, and then 31. So negative 315 is my answer. That's what I would get. Actually positive, because the negative divides each other. Use your calculator, folks. So that's what we get. That's one way to do this problem. A whole nother way to look at this problem is to actually engage the summation situation and find the a sub 1, the a sub 2, the a sub 3, and do that. And I don't know if you guys want to see me do it, but let's see what we can do. So we know that we can do it even if we don't remember a formula. We would be adding up 5 times 2 to the 1 minus 1, 5 times 1. So that's the first term, 5, plus 5 times the next term would be 2 to the 2 minus 1, which is 2, which would be 10, plus 5 times, and you get it. This is going to be 3 minus 1, which is 2. So 2 to the 2 is going to be 4, and 4 times 5 is going to be 20. So instead of writing 5 times 4, I'm just going to write 20. And so you can see we're multiplying by 2 each time. So this next term, again, when I put the, I just did 3, so if I put 4 in there, it's going to be 2 to the 3rd, which is 8. 8 times 4, times 5 rather, is going to be 40. And then do it again, it's going to end up being 16. 16 times 5 is 80. And did we get 1, 2, 3, 4, 5? I got to go all the way up to 6. 6 minus 1 is going to give me 5. And that's going to be 2 to the 5th, which is 32. And 32 times 5 is, I can do the math, I promise, kids, I promise, is 160. And I know it would have been easier if I just multiplied by 2, but this is what we're doing. So we could find those values, which would be a sub 1 through a sub 6, and then just add them together. And again, we get 315. So here we have another example. Example 3 uses an alternate formula for the sum. So in this problem, we are given, we want to find the series, find the sum of the geometric series for which the first term is this, and a sub n is this, and r is this. So what you're going to notice is that r is a fraction and it's negative. So what we're going to have are numbers that are going to get smaller and smaller in a sense, but then the sign is going to change over and over again. So if you're looking at this, you can kind of catch that sense. So you guys remember we just talked about these two types of formulas that we can use, and in essence they're the same. You notice that if we were to distribute through with a sub 1, we'd simply get this particular equation. But the problem with this equation is that it is only useful if you know the n value, and we don't. So what we're given is the first and last, the a sub 1 and the a sub n term, and we have the r value, but we don't have what n actually is. So this is going to require us to use an alternate formula. So what we're going to do is recall from when we were just trying to find the nth term of an geometric sequence, how we did it. We would start off with a sub n is equal to a sub 1 times r to the n minus 1 power. You remember that, just the last section. And so what we're going to do is play around with this equation. So if this is the case, we accept this as fact. If I multiply both sides by r, what happens? So on the left side, I get a sub n times r, which is fine, is equal to, now what's happening here? R to the n minus 1 times r to the 1. Remember, same base, we add the exponents. We get that we have on the right side a sub 1 times r to the n. These two are equal. These two are the same. And because of that, right here in this equation where I have a sub 1 to the r times r to the n, since it's equal to a sub n times r, which looks weirdly the same but not, right? Because if you like put a 1 here, anyway, my brain. Okay, so if we have this and this being equal, I can replace this with this. Why is that beneficial? Well, this is beneficial now that I've done that replacement, because with this replacement, I now can solve the problem because I am not relying on knowing n. I just need to know what a sub n is. Cool? I hope that made sense. I'm going to slide this over and we're going to do this problem in no time. So now we can calculate s sub n being s sub, we don't know what that is, but we can calculate the sum by recognizing that a sub 1 is this large number, 15,625, and I'm going to subtract to that a sub n, which is negative 5, times negative 1 over 5, and in the denominator, I'm going to subtract 1 minus that negative 1 over 5. I'm going to employ my calculator, and I get that the sum is going to be 13,020. And a couple things that might hold you back in doing this is, fooling around with these fractions. So I know that that's hard. You could definitely use decimals, but you have good minds and you guys can figure this out. In the denominator, we would end up with 6/5. I can't write it there, 6/5. And in the numerator, we end up with something like 15,624, and after calculating all of this. So because this really ends up just being 1 and we subtract 1. Hopefully that made sense. Let's go ahead and do this last example here. So in this case, find the first term of a sequence. We'll find a sub 1 in a geometric sequence when we're given this information. And so you know what we're going to do. We're going to pull up that formula where a sub 1 is a variable, and we're just going to fight the good fight. So we're going to substitute and place the s sub 8 value here, 1 minus 3 to the 8th over 1 minus 3, and a is our variable. With a little bit of calculator work, we get that the 39,360 is actually equal to a sub 1 times 3,280, I believe. And with that, we're going to divide both sides by 3,280, like so. And then we will finally get that a sub 1 is equal to 12. And thus the first term of the sequence is 12. Let me know if that made sense, guys. I look forward to talking to you all soon. Take it easy and take care. Bye-bye.